We've mentioned that batteries are really nice and that they maintain a constant voltage. Okay, so we said they've had some delta V of the battery that is constant as you hook it up to different things, a laptop, a calculator, a phone, and therefore in designing that device, they can control everything knowing that that voltage is constant. That is mostly true, and to many applications, it's true enough. But there's a problem, especially when currents start to grow. So when you start having things that take a lot of current, the battery actually will not produce the same voltage, not because this chemistry changes, but because it has internal resistance. Now that we know about series resistors, we can kind of analyze that. Let's suppose I have this battery hooked up to a resistor, just a single resistor. This could be a light bulb or a washing machine or something like that. And my battery from the plus end to the minus end has a delta VB. Okay. Well, doing my circuit analysis, doing my loop rule, I could see that the potential drop across this resistor is going to be equal to this, only opposite direction, and that the current is going to obey Ohm's law. So I'm going to end up with I equals delta VB over this resistance R. Okay. Well, that's an ideal battery. But a real battery, you can imagine it broken up into two pieces. You can imagine it having the chemistry that creates the voltage, and because of losses that happen, even in chemical reactions, a small resistance. We give it a little r. Now, these are all together in the sense that the chemistry is throughout the battery, the resistance is inside the chemistry and stuff like that. But you can break it up qualitatively and then quantitatively as if it's two separate effects. Now, I've been not talking about this weird cursive E, and the text says, that's the EMF of the battery, and it's because it's really annoying. It doesn't make any sense. It's a historic name that actually is kind of annoying when you try and think about what it's really doing. But this EMF I'm going to use in this case to differentiate the kind of the supplyable voltage of the battery versus what's actually ends up coming out of the battery. Okay, so this is the ideal. If there were no resistance, these two would be the same. This is called the EMF, and it's inherently what the chemistry could push. All right, so with that in mind, this is our battery, and we basically now have two resistors in series. Okay, so by doing that, we saw before that resistors in series are equivalent is the sum of the resistors. So now we have for what the battery sees, this pushing power, what it sees is two resistors with an equivalence equal to their sum, which means the current flowing is now smaller. Okay, so we have we have the EMF divided by R plus R. Okay, so we now have that current flowing. So now I want to find what delta VB of the battery is. Well, delta VB of the battery is going to be equal to the EMF minus, since I've got current flowing across this resistor, minus I times R. Okay. And that I we just found was this resistance here, so this equals EMF minus the EMF over R plus R. Okay. And I get a loss of the actual potential by this much. So if R is 0 for an ideal battery, this term goes to 0, and I just get the EMF equals the actual voltage across the battery. But as this grows, this gets less and less and less. Now, thankfully, this number is usually fairly small compared to outside loads, outside resistance. For example, a traditional light bulb, might have a fairly large resistance, um, and this resistance might be a very small resistance in comparison. And so thankfully this number is usually fairly small anyway. We get a small number over a big number, gives us a fairly small number. But as the current does grow, that effect becomes a little bit more noticeable. Okay. Um, and so this is how we design an ideal or a real battery, is we recognize that there is a potential drop within the battery that's equal to the current times this internal resistance. And we can find that internal resistance by actually measuring the voltage of the battery for very small current, almost zero current, and then measuring it for a non-zero current, and then be able to find that resistance. So there's different ways of analyzing this.